Namaste. In our constant journey towards providing a secure computing stack for our country, the Shakti team has achieved yet another milestone wherein we have showcased a complete secure execution environment starting from the micro boot that happens when the processor is executing at a machine mode at the boot, and then a secure boot that happens on top of it, which loads the indigenously developed separation kernel at the hypervisor mode of the architecture. And then today we have actually signed and booted the entire Linux platform. Why this is very important for our country? As we are moving towards the IoT era, we are seeing a ever increasing percolation and deployment of microprocessors at every stage, and there needs to be a very well defined security at these stages. Many times the software used in these microprocessors are proprietary and we don't have an access to the source code. The provision of an indigenous separation kernel which will help one monitor every interaction that the upper layer, namely the operating system and the applications, have with the hardware. This will provide us necessary infrastructure to monitor the security of the system. From a market point of view, this is extremely important. I take this opportunity to congratulate the entire Shakti team for bringing this together, and I am sure this is going to be a big turning point in providing a secure Atmanirbhar computing environment for our country. Jai Hind.
The Shakti Processor Initiative is an initiative that has actually been started a decade back in Reconfigurable Intelligent Systems Engineering Lab of the Department of Computer Science in IIT Madras. This initiative is basically targeted towards developing indigenous processor for India's specific needs. This particular processor is based on the RISC-V ISA. So RISC-V ISA, among the various ISAs that are available in the market today, has a lot of advantages, namely it is scalable, it is extremely modular, it is completely open. The main aim of the Shakti processor is to have different variants of it targeted towards the different use cases with this particular processor. What we are actually trying to show here, the secure Shakti. So the basic essential features of this secure Shakti processor is to have security inbuilt into the processor in such a manner that the entire stack of the SoC, right from the processor to the highest level application, is basically gets verified and ensured that there are no compromised images or no malwares that are possible to be present in the image when it is actually running.
Secured C-class, as Vasan rightly mentioned earlier, so this is one of the important variant of Shakti families of processors. The security is a very important aspect when we talk about open source architecture. It's not only just because it's an open source, it's also very important to compete with the market where the RISC-V is going to rule the world. In terms of the semiconductor industry, yes, RISC-V is the future of the world. RISC-V is the open source architecture, isn't it? As open as it is, we have to make sure it has to be as secured as it is. In the process of securing our Shakti variant, we group of people came together and sat, brainstormed what can be done next. This idea of just why don't we just make an end-to-end protection of our Shakti C-class. When I say end-to-end protection, so it's not only about building a fence. At the same time, having a watch of your kernel. Start from the place where you encrypt the booting process from the boot ROM and the U-boot, again adding another layer in between. Then at the end, your Linux kernel is booting up. So even that kernel, the Linux image, has been signed and encrypted using various algorithms, SHA-256 and RSA 2048 and AES. These are all the various aspects of secure C variant of Shakti, which our people is going to demonstrate you how it actually works, how each and every phase of the chain of trust has been implemented in this little proof of concept which we have done, so which we will be going to see.
The lowest level in this chain of trust is the hardware high assurance boot. High assurance boot aims to protect computer systems by detecting and preventing the execution of modified binaries. This enforces the exclusive execution of authorized binaries on the computer system. High assurance boot aims to mitigate bootkit and rootkit attacks. This requires that any binary that attempts to run on the system is signed by a cryptographic hash function and a public key encryption. The lowest level in this chain of trust is the hardware high assurance boot. High assurance boot protects computer systems by detecting and preventing the execution of modified binaries. This is achieved by ensuring that only authorized binaries are allowed to run on the computer system. This can also be achieved at higher levels of software abstraction. A secure boot requires that any program binary that attempts to run on the system is signed using a cryptographic hash function and a public key algorithm. This requires that the host system has a private key to sign the binary and the processor has the corresponding public key to verify the signature. The secure boot framework aims at mitigating bootkit and rootkit attacks and also other unauthorized firmware from running on the processor.
Once the hardware high assurance boot is completed, the resulting untampered program consists of supervisor binary interface bootloader and a universal bootloader. The supervisor binary interface bootloader, called OpenSBI, is an open source implementation of RISC-V supervisor binary interface. OpenSBI is a firmware that runs in the highest privilege mode, and it does jobs like initializing the hardware, and then it waits for the lower code that runs in lower privileges like the operating system, etc., to call into it to perform some critical operations. U-boot is a universal bootloader that is in general used in embedded devices. It is used to load the next stage, that is the kernel. It contains the instructions that is required to be run to boot the kernel. In our case, we use U-boot to do verification of the kernel before loading it. The procedure is very similar to how it was done in the previous stage. The hash of the kernel is calculated and then it is compared with the already signed hash that is present along with the kernel. This ensures that the kernel is not tampered by anyone and it is trusted before we load it. Thus completes the second stage of verification.
Now let us see about the hypervisor. With such stringent implementation that hinders the boot of a tampered image, we can be assured that most of the attacks can be prevented and the security has definitely been increased. But there are few possibilities where a malware can attack the sensitive memory regions of a kernel. So in order to protect this, there is a concept where hypervisor comes into play. Generally, operating system has its own abilities or security features like ASLR, which is the address space layout randomization, and other few features that will prevent the sensitive memory region access to the user. There are few malwares that can take the privilege of the kernel and then can try to attack the system from the kernel privilege. In order to prevent this, there is a separate layer called hypervisor that is being given to the whole stack, where it will prevent the sensitive regions of the kernel. The hypervisor kernel protect can include few security features like securing the sensitive data and the address of the kernel memory protection, and to ensure that there is no privilege escalation made, and to ensure that the hardware features that have been given by the kernel is not tampered with. To secure the kernel, we need to protect these critical data and memory regions, which the hypervisor layer will take care of. Once the hypervisor detects a malicious entry of a malware, it will block its usage or access to the memory region, and the details will be reported to the user by a user interface.
Here we can see that the process of booting has started. The bootloader has been copied from the SD card and the cryptographic algorithms have run. The digest is being compared with the signature is being compared with the digest calculated by the algorithms, and boot has been successfully authenticated. This has successfully enabled OpenSBI to start loading.
Here we can see that OpenSBI has started running and U-boot has started running here. And as we can see here, U-boot first calculates the hash and then it verifies whether the hash is correct, and here it has said OK, which means the hash was correct and it has matched, and hence then it says loading kernel image, and then it starts loading the kernel.
Once the U-boot verifies the hypervisor and kernel image, you can find that the SecV logo is being printed here, and below that you find that SecV has also in turn booted the Linux kernel image. So if we scroll down and see, we can find that there is the build root logging that is readily available.
In case the image, that is OpenSBI, that we upload to the bootloader is tampered, we see that the hash doesn't match, and because of this the boot fails and OpenSBI doesn't start.
So here we can see that when U-boot is loading Linux kernel, it is saying verifying hash integrity, and then it says that hash doesn't match. This says that the Linux kernel has been tampered with, and hence U-boot stops the loading at this stage itself, and it does not allow a tampered kernel to load.
So in order to show the protection, now we see that when we enter mod probe lksm will enable the hypervisor to be activated inside the kernel image. We can enable diamorphin by using the command mod probe diamorphin. That will enable the diamorphin rootkit to go and access the sensitive memory regions of the kernel. The hypervisor will prevent. So let us see what happens when the rootkits like diamorphin attacks without having the hypervisor protection. So here we have not given mod probe lksm, which will not initiate the hypervisor, and then when I directly go give mod probe diamorphin, you can find that the diamorphin has been initialized. So now that we are in the root of the system, we can exit and come back to as a regular user. So I am going to enter the username as IITM, and we can find that it has been logged into this user. So what diamorphin does is that it will give the root access directly without having the need for a password, just when it encounters the -64 in any of the commands that we give. So for example, if I give kill -64 space 0, this is a command that is used generally in Linux to kill a process. But now if I click ID, you might find that the user that was initially given the ID to be whatever it was IITM now has the root access without even wanting to enter the password. So this is where we find that how rootkits can attack the sensitive regions without the user's authentication, and hypervisor will protect this.
What we have actually attempted to do is to highlight how the secure Shakti variant could be used to protect the entire stack, right from the functionality available inside the processor all the way up to verifying the operating system that is actually running on the hardware. So with this we achieve security for images available only in the flash, and also when the images have actually been loaded and running, by dynamically protecting the memory at runtime. We hope this secure Shakti variant would actually be very useful in building different kind of secure products that would be typically required, especially for strategic use. Thank you.